All righty. Now let's see. It's gonna be chapter 17. Let me just go this. Chapter 17 for this is physics 102. Okay, supposedly, so this is going to be talking about interference and the principle of superposition. So supposedly we have, let's say you got a wave. Actually, let me actually put the units down. So this is actually 1, 2, 3. So you got your first wave. I'm just gonna do a sound wave because it'd be just easier to explain this on a sound square wave. So let's say you got this one little fellow over here that's going on in this direction. And you got another wave that's actually 2 units high going in the other direction. So when they go ahead and they meet up, so you got this one over here. So they're both gonna go in and interfere with each other. So after a while, actually, let me use this one. Awesome. So you got your first green wave that's going in, and on top of it is actually meeting up with the red wave going in. So this is the first unit for the green one. This is the second unit for the red one, and this is going to be your resultant wave. So you get 2 waves coming in. They're going to meet up. So basically, they're adding up. So this side is adding up to this side right now. So let me go back on here. Actually, let me just copy this. So you got 2 waves meeting up. You got your green wave and you got your red wave. Meeting up there, they're both gonna be constructive. So basically, so this side is gonna go along with this side. So that's gonna be 1 plus 1, another 2 units coming back to 2 units. And again, you got your green one is going that way, and your red one is going the opposite direction. That's until they meet up. And once they meet up, they can the wave would look, the actual wave would look something like this. So let me get this. So when they beat up, you get one big super wave coming in. Now, right before they meet up, and that's what we actually, hold on, let me just define, and that's what we define wave interference. So your wave interference wave interference. That's when you have 2 or more waves overlap in the same region. So you got two more waves going in, and they both overlapped in the same region, which caused a big superwave. So the question that we have is, what is the total wave look like? Now your total wave is going to be whatever wave equation you have for the first wave plus whatever second equation you have for the wave. So question, or you can say another question. What these two waves look like when overlapping? So let's go on these two waves, and right before they overlap each other, so we got these. Let's say we do them right before they overlap each other. Let me get on a different piece of paper. So let's get our little black line on our equilibrium line. So when they both went, so you get the little green wave is going in. So that one, let's say they interfered. And this is the line for the first one. This is the line, second unit, and this is the line for the third unit. Actually, hold on. So this one is going this way. The other wave, while it's coming in from the other side, overlaps for it. So let's say it overlaps and like right. Oof. Okay, third time at the charm. Let's say you got two waves looking like this interfering. Well, so what the total wave over here right now would be. So I'm actually going to use blue. For the first wave is going in the same one. But at this point, you got this green wave coming in with this red wave over here. So that actually going to go into a third unit. Coming in up until this point, that's where it's going to actually fall down. Going in, and it's going to fall down. So our new wave will look like something like this. Let me just go in. So when they overlap, this is the total wave that we're getting in overlapping. It will look like something like this. Actually, this should be a little slower, a little shorter, I would say. Yeah, that's better. Now, while the waves overlap, because, so while waves are overlapping, that happens because they get distorted. Distorted because of the total wave will be the sum of the two waves. That's what we just saw. Now your electromagnetic waves go through each other. Like what we just saw, and creating one big wave. Now, again, for this wave that we draw, for that 1 second they overlapped. You still got the green one going in on that side, and you got the red one going in on the other side. Now, although they meet, the shape before is going to equal to the shape after. So the shape before is going to equal to the shape after. Now, one thing we do, just because we have interference, that means we do not lose any information while overlapping. So whatever you're using, your cell phone, your text, could you imagine if you actually overlap other waves and all the information go in, it'd be a disaster. But actually, in real case, the waves do not exchange information when you actually have an overlapping. But the wave interference is happening while overlapping. But the information sharing is not happening. So the wave interference is happening while overlapping. So the waves, basically, they go through without being affected. So the waves make it through unaffected. Now, supposedly you have two sources of waves. Let's say you have, actually, let me do black. So this is your wave source 1. And let's say this is our equilibrium line. And let's say I'm going to get a different color for wave source number 2. That's my wave source number 2. So you get your source wave 1, source wave 2. I don't know. Let's say it's 2 speakers going in. So this is going to be your, actually, let me write this down. This is going to be your equilibrium line. This is this equilibrium line, which is the wave would be 0. So this is your source Y1, and you're getting a wave that's going in. And this is your source Y2 is going also another speaker. You're having another wave going in. Well, if you actually added them up, your total wave, let's say this is the 1 and 2 sources, will look something like this. Actually, let me actually copy it and paste it. So copy, let me just copy the first one. So this is your first one. And let's say you copy and paste, let's copy and paste the second one. So they are interfering. Now, I'm going to try to line them up. So what do you notice? You notice that there are in phase. So this is when it's in phase. Let me write this down. So you notice that these 2 points over here and these 2 points over here all meet up. And what you're going to end up having is having one super wave going in. So really, for these, when you add them up, when you have an interference on both of them, so let's say 1 and 2, you're going to have a bigger wave going in. And so because they're both in the same phase, right, when you put them in, you're going to create one bigger wave. And that's what we call constructive interference. So this is going to be constructive interference, which means you constructively combine to make a big wave. Constructively combine to make one big wave, which means your ear, I guess your ears will be right over here. So basically you got a speaker, let's say you go to the club and you go have a speaker that's actually playing music, and right next to another speaker sending the same music in the same wave, you're gonna hear it as louder when it comes to your ear because of the both constructive interference. So basically, you're gonna hear a loud sound. Now, supposedly we have the same thing, but let's say our waves right now are out of phase. So let's say you got your source one, that's going a wave like, and here's your equilibrium line. Wave source 2. Actually, this is a little bit big. Now, this one's going to be out of phase. So let's say it's 180 degrees out of phase. So let's say this one goes from the bottom. So what would happen? Let's say you take this wave. Let's say this is going to be your interference, 1 and 2. So first of all, you get the first wave. I'm actually going to copy paste it. So you get your first wave over here. Copy, paste. And then let's say when you actually go in on the other wave, let's say we pick this up. Yeah, here they are. They start over here. Now, what do you notice? You notice that the nodes actually are opposite of each other this time instead of being in the same time. So this one is this one, this one, this one. Basically what they do, they cancel out, right? So they cancel out. So all you have is just an emptiness. That's what's called a destructive interference. So your ears are over here. Okay. Now you got 2 sources that putting 2 waves opposite each other, 100%, 180 degrees out of phase. Now, if you you can listen to each wave source by itself. It's no problem. When you have actually had both of them, they both cancel out, so you don't hear nothing. So the noise are canceled out. Or the waves cancel out. And that's what actually works in a noise canceling headphones. Now this is called a pi shift. So basically, each amplitude cancels the other amplitude, and each trough cancels the other trough. So valley with the valley and the top with the top. Now, if you noticed, if you actually actually, let me just go in over here and copy, paste. Let me actually take this out. All right. So now if you got two waves, and let's say you get this one, let's just take one of these waves. Copy, paste. So what would happen? Well, if they overlap on each other coming up from the same source, what you're gonna have? You're gonna have a constructive. If you go half a wavelength, it's gonna be destructive. If you go in, again, it will be constructive. So notice if you go one wavelength, okay, that you're gonna have a constructive, and then you're gonna have destructive. You got another wavelength constructive, half a wavelength destructive. If you start actually from the same phase, let's say, I'm just gonna erase this one over here. So let's say you got on the same phase. So you go and start with the phase, that's destructive. You go half a wavelength long, that's destructive. And a wavelength long, that's constructive. My drumming is not that great. Half of wavelengths is destructive. So let's say our source is, for the second one, is right over here. So actually, let me actually draw the source. Let's say the source has moved. We got one source over here and another source right over here, source 2. And basically, this is your ear going in. So let's say this is your distance from this first source wave to your ear. That's your x1. And the distance from the second source to over here, that's your x2. So delta x, we said it's going to be x1 minus x2. Now, if what we got is 0 lambda shift, 2 lambda shift, 3 lambda shift, etc., that's what we call constructive lambda. And the same thing, if we actually take this and we move it, you're going to have a destructive. So your delta x, in this case, which is your x1 minus x2 is going to equal to your 0. Not 0, I'm sorry. It's going to be half a phase. So it'll be lambda over 2. Two lambda over 2 is going to equal to lambda, is going to equal to construction. This is going to be 3 lambda over 2, 5 lambda over 2, etc. That's your destructive lambda. If they both start in phase, that's two sources start in phase. Okay, well, let's say we have two sources that does not start in phase. So let me actually go over here. It'd be actually easier just if I copy this. So this is going not in phase. So this is actually the, yeah, this is actually gooder because they're not in phase anyway. So when they are not in phase, let me just get this out. All right. So let's say you start off this one out of phase. So you start like this. So if you actually move half a wavelength, they become in phase. If you have another half wavelength, they become out of phase. Half wavelengths, they become in phase. So basically, if you start out of phase, it's actually the opposite when you have two sources starting in phase. So for our example, and this is starting out of phase, your delta X which is your x1 minus x2, which is going to equal to your 0, lambda, 2 lambda, etc. This is going to be destructive. When you go half a wavelength, which is going to be lambda over 2, 3 lambda over 2, 5 lambda over 2, etc., that's going to be constructive. And this happens, again, when two sources start out of phase. And that's basically what we did, right? When two pulses merge, the slinky, which we actually have a lab with the slinky that you're actually gonna be able to do this. But when two pulses, when the pulse merge, the slinky assumes the shape that is the sum of the shapes of the individual pulses. Over here, we had a pulse, we did a square pulse just to make it a lot easier to explain. When pulses merge, the shape of the slinky, the sum of the individual pulses. So both of them take a little pulse at that 1 second, that's actually the sum of both of them, and then they both go in without actually exchanging any information. So that's what gets us to the principle of linear superposition. When two or more waves are present simultaneously at the same place, the resultant disturbance is the sum of the disturbance from the individual waves. So when two waves always meet, condensation to condensation, refraction to refraction, they're said to be exact phase. And they do a constructive interference. That's what we just showed a little while ago. And when two waves always meet condensation to refraction, they are said to be out of phase or exhibit destructive interference, and that's what we just saw. So go ahead, there's a little example over here that you can actually go ahead and start working on, see if you know how to do it. This was just calculate the wavelength that's coming in from both speakers. We're going to be talking about diffraction in the next. We talked a little bit about diffraction in beats, but we're going to be talking in the last chapter. We're going to be talking more about diffraction in the next chapter in detail. That would end chapter 17 for this one. If you have any questions, just email me at abunaem@uah.edu, or you can give me a call at 256-348-1480. Thank you.